Okay, yeah, thanks for the invitation to be here. So my talk today is atoms interlinked by light, from quantum metrology to topology, and it's a talk about experiments where we let atom clouds in a cavity talk to each other via photons. And the broad motivation is sort of having... So broadly, we're motivated by the general notion that having access to actually non-local connectivity in quantum systems can enhance our toolbox for actually a range of tasks. So one area is in quantum metrology. It can give a way of kind of efficiently generating collective entangled states. And so you probably heard something about that already in, for example, James's talk. And if one sort of has sufficient programmability, in addition, that could perhaps allow you to kind of optimize your quantum sensor for particular metrological tasks. Another set of directions is in computation. So non-local connectivity can improve the performance of error-correcting codes, or could be a way to, in a hardware-efficient way, solve certain optimization or constraint satisfaction problems that sort of naturally map the systems with non-local interactions, like the non-local interactions between queens on a chessboard, and this work from Helmut's group. And then another sort of class of directions are in quantum simulation. You heard this morning about beautiful work on spin glasses from Ben Lev's group. I think folks in the audience, such as Sebastian Diehl, have thought about ways of using non-local interactions in a cavity to stabilize spin liquids. We've explored building kind of exotic toy models of quantum gravity, and you heard about sort of motivation for flat bands, which can be engineered with the help of having kind of beyond nearest neighbor connectivity. So those are all kind of directions that one might like to go by having some quantum system with programmable non-local connectivity. Broadly speaking, there are sort of different, I would say, two main classes of approaches to doing this. One of them is move your atoms around in order to sort of go from something that physically is local connectivity, but effectively is non-local. Or the other one is have atoms coupled to a single delocalized mode of light. And that then is a way to very sort of naturally get non-local connectivity, which in the simplest case, if you're just dealing with a single mode, will be all-to-all connectivity. And that's great for some applications, but sort of my talk will be focused on can we go beyond that and also kind of sort of maybe break down this all-to-all connected graph and get to more programmable connectivity. And so I'll talk about kind of a set of tools we've been developing over the past few years for having programmable interactions and programmable entanglement in a system with an array of atomic ensembles. I'll talk about recent work applying programmable entanglement towards tasks in multi-parameter sensing, and applying programmable interactions towards to kind of enrich the toolbox for studying topological physics. So that's where we're going today. And the basic building block of everything I'll say is the notion that if I have, for example, just two atoms in a cavity and I want them to talk to each other, one way to do that is a photon-mediated spin exchange. So spin-up atom gets converted into a spin excitation gets converted into a photon, which gets converted into a spin excitation in another atom. If this is, and those spin exchange interactions can be as long-ranged as my cavity mode is delocalized. In the simplest case, when I scale this up to n, I'll have all-to-all connectivity. And then we're going to ask, can we start to kind of make that more programmable by adding in optical control? And so in some sense, I think of this as kind of merging two sets of tools. One is this very well-established toolbox for generating collective entangled states by having many atoms talk to a single mode of light. And James may have told you about some of his work on, for example, making states that are useful for atom interferometry. This is well-established also for starting to, at least at the proof of principle level, enhance atomic clocks. So this is sort of a very, powerful toolbox for entangling many atoms at once in a scalable way. For example, squeezing the quantum fluctuations in a way that's useful for metrology. And then sort of there's been this parallel set of developments of actually applying local control and detection to cavity QED systems. I think you'll hear probably from Dan this afternoon about controlling and detecting individual atoms in an optical cavity. And in our work, we've been working with clouds of atoms that we can locally control. So bringing those two things together, the experimental platform looks something like this. We work with an array of anywhere from a few to 20 clouds of atoms that it's not drawn in here, but they're pinned in a lattice inside the cavity that's in registry with the cavity mode. But in addition, they're sort of grouped into these little clumps by a set of transverse tracks. And so we have these clumps of atoms that have around 1,000 atoms per site. We're borderline in the strong coupling regime for single atoms, but this means we have a large collective cooperativity per ensemble. And when we want to turn on interactions in a controllable way, we send in a drive laser that, so that process where you flip a spin and put a photon in the cavity, that's a Raman process controlled by involving a drive laser and emission into the cavity. That process isn't resonant, but then the pairwise process where that photon is absorbed by another atom is resonant, and that gives us interactions. And then in addition, we have a laser that can come in from the side and implement local spin rotations on any site. So that's our ingredient of spatial control. So just to go a little bit more into the dynamics of the cavity-mediated interactions, we work with rubidium atoms, and we have a spin 1 ground state. And so often the way that we probe this system, at least for the first part of my talk, will be we start with all the atoms in the m=0 state of the spin 1 ground state. And when we send in light, that can mediate a process where basically now two m=0 atoms turn into a +1 and a -1 atom. So this is a way of generating correlated atom pairs. It has a longer history of being studied by collisional interactions in Bose-Einstein condensates, but here these are long-range interactions that can be between any pair of atoms in sort of the millimeter scale Rayleigh range of our cavity. So one way to see, actually, if you want to check, are these interactions in fact giving rise to entanglement, we can look for squeezing of quantum fluctuations. And so it turns out one has to look in what to me seemed like a sort of a weird phase space to see this squeezing. You might be used to thinking about some block sphere of a collective spin with axes fx, fy, fz. Here the axes are a little bit different. This QZZ axis is basically the population difference between the + and -1 and the 0 states. So we start polarized in this direction when all atoms are in the 0 state. And actually the details of this phase space won't matter except to say that the spin exchange interaction looks like a collective fx squared plus fy squared. That fx squared term generates a twisting about the x-axis on this sphere, and that can kind of squeeze the quantum fluctuations. So we should expect that if we measure noise as a function of kind of rotation angle, where rotations are generated in our system by a quadratic Zeeman shift, we will see the noise hopefully dip below the standard quantum limit of the unentangled state, and indeed we see that effect, and so that shows that this kind of cavity-mediated spin mixing process is in fact generating entanglement in our system. This idea of doing this in a cavity with photon-mediated interactions was first proposed by Parkins in this paper back in 2017. So so this is the first step of having sort of the global entanglement, but now we want to go in and start applying spatial control. And so just to kind of broadly motivate that, why do you even care about spatial control? Some of the applications where we use atoms as quantum clocks or sensors can benefit from the ability to, for example, compare different clocks, like different clocks at different heights in the gravitational field, or actually sense something with spatial resolution, like imaging magnetic fields. And so to optimize the performance, multimodal entanglement can generally be a resource that's of interest. We actually, I'll focus in today's talk on using this approach of starting from global entanglement and breaking it down by adding in this ingredient of local control. And so the basic idea is, the global entangled state is great if I want to sense a global field. If I wanted to sense a magnetic field gradient, the simplest thing I might do is take my global entangled state, but rotate like the spins on the right side by pi, so that I'm now sensitive to gradients between the left and the right. With some more sophisticated control, there's also a way to map this to like independent entangled states. But what I'll actually talk about to kind of illustrate the programmability is preparing a class of states called graph states, which I can essentially describe as I have a graph that specifies the structure of correlations between nodes which are my atomic ensembles. The minimal instances of this
is if I have two nodes with correlations between them, that would be EPR type entanglement, and I'll give an example of using that in sensing. So quite generally, though, just to be a little bit more explicit about what I mean when I draw a graph, if you kind of have a quantum information background, you might be most used to thinking about this in the context of qubits. These are also called cluster states, and they're the states you would get if you had a qubit on each node of a graph in like a superposition of spin up and spin down, and you had Ising interactions on all the edges for a fixed time. And that would give you correlations between sigma x and sigma z on neighboring sites. So the version of this that we're going to be thinking about is more inspired by like photonic systems where one deals with continuous variables. And the reason for that mapping is we're dealing with these large collective spins, which to lowest order, we can just think of in terms of the quantum fluctuations in the two directions transverse to the mean spin. I'm just going to call those directions x and p, right? So I'm going to kind of think about a region on that spherical phase space that's roughly planar, and we start with some Gaussian state, and the graph state is going to be the one that you would make by having the specified graph having interactions that look like xi, xj on all edges of the specified graph. And that would give you correlations between x on a given site and p on the neighboring site. So now the question is maybe, in our system, we don't actually introduce arbitrary pairwise interactions. We use these global cavity-mediated interactions. So if you give me a graph, do I actually have a way of making it? And the neat thing we realized is if you give me a graph, I can write that out as a matrix. And what I can do is I can diagonalize that matrix. Here's a simple example for this EPR type state of just two modes. And the eigenvectors that I find will actually be collective modes, which are the modes that I should squeeze to make this state. So I've mapped this onto a set of collective operations. I should squeeze, in this case, the symmetric and the anti-symmetric mode. And the eigenvalues, here the eigenvalues would be plus and minus 1, which tell me actually which quadratures I should squeeze. So the eigenvalues in this case tell me I should just squeeze orthogonal quadratures of these two modes. So that's a prescription now in terms of collective operations that are very natural to do in a cavity. To make this EPR entangled state, I will do a global squeezing operation. Then we do a local pi rotation. So in this case, physically there are 4 atom clouds, but for now we're just treating them as the left and right subsystem. I call them A and B. We do our global squeezing operation, a local pi rotation on the B subsystem. We can also then do a phase space rotation. So the local rotation maps the squeezing from the symmetric onto the anti-symmetric mode. The phase space rotation allows us to now pick out which is the squeezed quadrature. And then finally, we do one more squeezing operation so that we've now also squeezed the symmetric mode. And so we have the symmetric and the anti-symmetric mode squeezed 90 degrees out of phase. And that was precisely our prescription for making this EPR entangled state. By seeing essentially that the noise of these two modes, the symmetric and the anti-symmetric mode, is if one actually looks at the product of the uncertainties in, let's say, x of the symmetric mode and p of the anti-symmetric mode, having that product be less than 1 witnesses entanglement between the left and the right. And so this shows we've made this this entangled state. And now you can also ask kind of, can you scale this up? So the fanciest looking graph we've made so far is this square graph of 4 modes. So the correlation matrix should look like a checkerboard. If we diagonalize that matrix, we find these 4 normal modes, which can all be obtained from one another just by doing local pi rotations. And so by a sequence now of 4 collective squeezing operations with local rotations in between, we can squeeze these 4 modes in appropriate quadratures. And from those curves, we can reconstruct what is the correlation matrix, and it indeed is consistent with making this square graph state. So I think that kind of illustrates this sort of general method for programming the graph of correlations. And now there's a couple of additional things we might want to do. One thing I want to first comment on is, so far, the amount of squeezing is fairly modest. It's about a factor of 2 per mode, and we might want to do better. And it turns out one way we can do better is actually recognizing that some of this, some of what's limiting us is actually not our ability to prepare the state, but our ability to detect it. And so we can actually use the cavity not only to do the initial squeezing, but later to actually amplify our signal to better let us detect, better let us essentially benefit from the squeezing. So the sequence looks something like this. If you're trying to detect some small perturbation, that's shown by this arrow in green, you first prepare your squeeze state that should be sensitive to that, you displace it, and then we want to kind of undo the squeezing and actually amplify our signal. So we can do that by doing a pi by 2 rotation, so swap the squeeze and the anti-squeeze quadratures, and now repeat the cavity-mediated interactions to actually amplify our signal, and now the noise we need to detect is also just the noise at the initial unentangled state. And that allows us to, in this case, extract about 7 dB of metrological gain. This so far is for the collective squeezing in our system, but the neat thing is we can now actually transfer this combination of squeezing and interaction-based readout to any spatial mode. So at least here's an example where we've now said, if I want to be sensitive not to just a global field, but to a spatially oscillating field, then I will map the squeezing onto this mode I call k equals pi, that has this spatially oscillating structure, with some local rotations before I try to sense that field, and later I can again use that same set of local rotations to map the squeezing back to the symmetric mode and amplify the signal in the symmetric mode. And by virtue of that fancier sequence, we can then also get this interaction-based readout to work for essentially, in this case, this k equals pi mode, or in principle, this could be generalized to any spatial mode. So one thing that's, I've shown you kind of how we can program the graph of entanglement and also use interactions to enhance the readout of these states. One direction that I think would be fun to explore with this is basically asking, in general, you know, if you're trying to do some maybe more sophisticated task than just measure a field or even a gradient, but say like classify images, classify spatial patterns in a field. There may be particular collective modes that are more informative than others. And this is generally true actually in image compression. The way one compresses an image is one says, I don't need to keep every pixel of information. I can keep sort of certain principal components that have the most information. So there's an interesting question here, I think, of asking for certain like imaging tasks, can one benefit from squeezing just some set of collective modes that matter the most? Another direction that this programmable entanglement is a resource for is actually, I guess imaging is one type of multi-parameter estimation, but another sort of even richer type of multi-parameter estimation is I want to have vector information about a field. And that might require actually sensing perturbations in non-commuting observables. And so another direction that actually these EPR states are useful for is precisely this type of task. And one thing I find fascinating here is there's even potentially a resource here for getting even an exponential speed up if one can do this for many spatial modes. So the general concept here is if I want to sense, let's say, two components, Bx and By, of a magnetic field, if I just, and I want to image, right, so I want spatial resolution, there's going to be some limit on how well I can sense both of those. That's just set by the standard quantum limit for however many atoms I have in a given pixel, right? So the product of uncertainties in these two components of the field will go as 1 over n. And even if I squeeze each of these ensembles, I can maybe win in one quadrature, but I'll lose in the other. So if I want to do better, the resource that I should use is to actually entangle these sensor regions. This is where I'm trying to sense my field with high spatial resolution. I could entangle them with some reference spins in this EPR type of entanglement. So why is that useful? Essentially, I now have a state that has reduced noise in the X quadrature in the symmetric mode, and in the P quadrature in the anti-symmetric mode. So essentially, because the sum of the X's and the difference of the P's commute, there's no uncertainty bound to how precisely I can know both of those. And if I design my system so that the B subsystem doesn't couple to my field, maybe it's a magnetic field in sensitive states, it's far away, then actually there's no limit to how well I can detect these two components of my vector field in the A subsystem. So that's an idea that sounds nice in principle, but has one potential challenge, which is I need to measure these non-local observables, the sum of the x's and the difference of the p's for these two subsystems. And the neat thing is the cavity actually does give me a way to couple to those non-local observables. If we want to actually detect these non-local quantities with spatial resolution, it's convenient to image. So what we want to actually do is we're going to let cavity-mediated interactions amplify the non-local observables, and then we're actually going to take a picture that allows us to access that information. So the idea is basically I'm going to prepare this EPR entangled state. I'm going to apply some displacement in phase space, which I've called alpha here, and now we're going to do a sequence of amplification processes. One is going to be to amplify the p quadrature in the antisymmetric mode. We'll amplify the x quadrature in the symmetric mode. And at the end of the day, what we'll do is we'll just read out each site. We'll just take an image where we read out actually in the 45-degree basis, which I've called Q. And because as long as we have sufficiently strong amplification before we do this readout, we can measure in this single quadrature that gives us, in the antisymmetric mode, we'll primarily get the p information. In the symmetric mode, we'll primarily get the x information. And so we can now reconstruct how strong the displacement was in any direction, the strength and direction of the displacement. So here's an experiment where we've done that. The sort of boxes are some initial displacement we applied. The circles are the amplified displacement at the end of the day. And if you examine essentially the signal to noise ratio, we can work out the sensitivity of our measurement as a function of angle in phase space. The green circle is the best you could possibly do without having entanglement with this reference system. And the purple points are our result. And this is better in area by a little over a factor of 2 than that ancilla-free bound, the bound of what you can do without the reference system. So far, this is a single EPR state, which has this funny interleaved structure, which just sort of happens to be how we set this measurement up. But it also becomes interesting if one could do some slightly fancier sequences and have an array of pairs of EPR states. One thing this is actually a resource for is if you have some kind of fluctuating fields and you want to characterize what probability distribution are they drawn from, or fluctuating displacements in this phase space picture. It turns out that this resource of EPR entangled pairs can actually give you an exponential speed up in sort of how quickly one can reconstruct that probability distribution as a function of the number of modes. So that would actually be a very neat direction to take this in and explore. And I think kind of illustrates something that I found sort of surprising about the power of even these sort of multi-mode Gaussian entangled states. Okay, so I've kind of illustrated this toolbox of programmable entanglement for maybe allowing us to explore some new directions in quantum sensing and multi-parameter estimation. In principle, this programmability, might have other applications. I mentioned computation early on. There, it would be best to have potentially single atom qubits with stronger atom photon coupling. So I just wanted to take a moment to say, can these types of experiments be taken in that direction? In the optical cavity, actually we foresee at some point in the not too distant future an upgrade to single atoms where it seems reasonable to get the single atom cooperativity to be something like a couple hundred, and that could be interesting, but still would be sort of limited in terms of how coherent these interactions could be. So there's a separate approach that we're also working towards in our lab where we've built actually a superconducting millimeter wave cavity that has to operate at 1 Kelvin. But if one were to trap an array of Rydberg atoms in there, which we haven't done yet but want to do, the cooperativity, single atom cooperativity, could be over 1 million, and that would be a very exciting and different regime. And so one of these days, maybe some of these methods can be also sort of translated into this type of system. Okay, so that would be cool. You could actually fit a very large array even in a single pancake of the standing wave. So you might ask, actually, how do these methods scale? And one of the things that I found a little bit surprising at first is you might think, like, if I want to have sort of a programmable graph of m nodes, it might take like m squared operations to control the pairwise couplings. But this sort of method of coupling different collective modes to the cavity, there are just actually m collective modes. And in principle, one can make any graph with sort of a sequence of M operations, each of which happens at a collectively enhanced rate. And so it's actually fixed into total interaction time. Some graphs are maybe a bit more convenient than others. One particularly convenient class of graph are translation invariant graphs. In that case, actually, these eigenmodes are just spin wave modes. And in that regime, we've actually in the past kind of used this approach. I maybe haven't always thought of it in this language, but this approach of actually coupling different spin wave modes to a cavity. One way you can do that is actually just apply a magnetic field gradient. You don't even need arbitrary optical control, and different spin waves you'll sort of, the k equals 0 mode at time 0 cycles to a different momentum at a different time. So that gives a way of kind of sequentially coupling to these different momentum modes and programming the graph of interactions. And that's something we've done actually at larger system sizes. In real space, the picture is essentially, if I turn on a magnetic field gradient, it suppresses the spin exchange interaction between any pair of atoms that's not on the same site. There's an energy cost to the spin exchange interaction in the presence of a magnetic field gradient. But if one has two frequencies of light with the appropriate frequency separation, the spin exchange interaction can be resonantly turned on in a controllable way. And this is a really neat way then for saying, you give me some translationally invariant graph you'd like me to engineer, and all I need to do is actually program a particular waveform into the intensity modulation waveform into my drive field, and it will realize that graph. And so here are some pictures of actually interaction graphs that we made in arrays of up to about 20 sites by this trick of sort of having a magnetic field gradient and control of the spectrum of the drive field. One can program the graph and also the signs, or in principle even the phases of the couplings. So this is a toolbox that opens up a number of different directions. You know, I showed on the previous slide some examples of graphs that you can kind of embed in 3 dimensions. We've also explored exotic coupling structures that can't be thought of as just embedding the sites in a Euclidean geometry, that make the system look like it kind of lives in a curved space and connect to ideas of quantum gravity. But another direction that I kind of want to, in the last few minutes, share is actually taking this toolbox and asking, can we use it actually for some explorations of topological physics? And here the general motivation is that one of the reasons for seeking topological phases of matter and to engineer and control them is that it potentially gives you a way to store information robustly in some non-local degrees of freedom. And then the question is sort of how do you actually manipulate and access that information once you've intentionally made it kind of hard to access by making it non-local. So there's this nice paper from a number of years ago saying, well, maybe we could actually use a cavity as a way to controllably talk to non-local degrees of freedom and access information that otherwise would be topologically protected. So, you know, the ultimate dream would be maybe some lattice of qubits where you can pick which string of qubits you talk to. We're not going to be doing that yet. But we wanted to sort of build the simplest kind of topological model we could in our system and start to explore this notion of using the cavity to measure something non-local. And so actually there's a couple different approaches you could use, either starting from a graph state. That could be a way to make some topological states like this Tora code state. Or the one that we'll take is using these programmable interactions to engineer a band structure that is topological. And the basic mapping I have in mind that I think is useful for thinking about this is the full system is I have these kind of collective spins, and I have spin exchange interactions where spin excitations can hop between sites, which are these atom clouds. I can roughly map that to some picture where I have something that looks kind of like a Hubbard model. I have some particles that can hop between these sites. Those are the spin excitations. And I also actually have some interaction between the particles on a given site. And so the cavity gives a way to program in what the hopping is. It also actually lets me control, do I have open or periodic boundary conditions? And I'll have a knob also for tuning this on-site interaction. And what we'd like to see is, can we also benefit from reading out non-local observables? Okay, so in general, actually having like arbitrary control of the hopping could be very cool and let you engineer flat bands, and we haven't explored that yet. We explored a very simple test case where we still have just kind of a nearest neighbor type of coupling. It's this dimerized chain forming the paradigmatic SSH model, which has kind of two key features that will matter. One is that there's a topological phase when this J prime coupling within the dimer is less than the J coupling between the dimers, which is characterized by some edge states, which are basically symmetric and anti-symmetric superpositions of the left and right edges that are well separated from the bulk. And there's a topological invariant called the Zach phase, which is, if one looks at the relative phase between the A and B sites, whether or not that winds as a function of momentum signifies whether you're in the topological or the trivial phase. So these are kind of the key features of this model. If we want to engineer it, essentially what we do, it's a little bit fancier than the translation invariant things I showed before because of this dimerization. So we actually currently don't just use a physical magnetic field gradient. We use light to imprint a spatially varying Zeeman shift, which in our case, so these local light shifts give us an effective magnetic field that has this kind of zigzaggy configuration I showed here. But the key point is it allows us to use two different frequencies of the drive field to control the J prime and the J coupling to form this dimerized chain. And if we want, we can use one additional higher frequency to connect the two ends of the chain. Okay, so this gives us a way to engineer this model. And because we're low on time, I won't go into details of measuring this topological invariant. But what I want to kind of illustrate is actually probing the edge states via a non-local cavity-based interferometer. So the story here is, first of all, it turns out everything I told you about this model assumed that there's no on-site interaction. To turn off the on-site interaction, which is basically on-site spin exchange, we actually have to play some clever tricks involving two drive fields, which are designed to cancel on-site interactions while reinforcing the hopping of the spin excitations. But if we do that, so this is this blue curve here, and we start with some spin excitations on the left edge, then as a function of time, we see the spin excitations hop to the right edge and back. So this is an oscillation of the spin polarization on one edge that signifies the presence of these topological edge states, or that's consistent with that. And if one turns on on-site interactions, that oscillation actually is suppressed. And that's something that I realize there's a kind of nice simple picture for understanding, which is to say, in the limit where I have sort of these two edge states and they're well separated from the bulk, I can think of this as actually a two-site Hubbard model, where the gap between the edge states corresponds to some hopping of spin excitations between the left and right edges. And if the on-site interaction is too strong, there's a well-known effect known as self-trapping, where the excitations will be trapped and not oscillate. So in the absence of on-site interaction on some block sphere, where the poles are the left and right edges, I get Rabi oscillations. But if I turn on this on-site interaction, these trajectories will change. I'll basically get two fixed points for strong on-site interaction at the north and south poles, or just, and the dynamics would be essentially precession about those fixed points. So that I thought was a nice picture for explaining the suppression of the oscillations that we saw. But to really kind of check the picture, it would be nice to measure not just the population dynamics, but also the relative phase between the two edges. And so a fun thing that we can do in the cavity is say, let me actually use my non-local coupling to directly form an interferometer that couples the left and right edges of my SSH chain. So we prepare some spin excitations on the left edge. We use the cavity to essentially form a kind of a beam splitter where those excitations can hop to the right edge. We then evolve under this SSH Hamiltonian and do one more beam splitter operation mediated by the cavity. And then after all this, if we measure the left-right imbalance, that will give us phase information because we formed this interferometer. And so by doing this cavity-based non-local interferometer, we can actually see trajectories in the phase space of this kind of left-right block sphere that match this picture of having essentially Rabi oscillations in the absence of interactions and having this self-trapping effect as we crank on the interactions. And so I think this is kind of a nice, it's mean field dynamics, but a nice kind of first demonstration of using the cavity to probe a non-local feature of a topological system. And at some point, it might be fun to also go beyond mean field dynamics and ask, can we, for example, look at the quantum fluctuations and see signatures of entanglement induced by this on-site interaction. Okay, so the kind of common theme between the two stories I told you, one in using programmable entanglement for sensing and one in exploring quantum simulation with these programmable interactions, is that the cavity actually gives us a way of controllably accessing non-local degrees of freedom, right? That was a crucial ingredient of leveraging this EPR-type entanglement for sensing conjugate quadratures, and it was also a crucial ingredient of probing these topological edge states. And so with that, I'm out of time, so I'll just briefly thank all the folks who worked on this, in particular these folks in red were the key people behind these cavity experiments. Yeah, take any questions.
Questions? Yeah, Jamir.
So a very interested question, you will recognize the origin of it. So when you start to crank up a little bit more cavity losses, can you start to make a Lindbladian that will have engineered dissipation? So a sort of synthetic version of what people call ER correlated emission in free space.
Yeah.
Do you have limitations to do that, and why haven't you explored already?
Why haven't we explored? Because we have too long a list of things to do, and all of them are, all of them are technically challenging and take time. But no, so in terms of can you do this? Yes. So normally when we want to focus on coherent interactions, what we do is we actually operate at some optimal detuning so there's that Raman process where you flip a spin and put a photon in the cavity. That process isn't resonant. We place it detuned from cavity resonance. And if we had actually infinite cooperativity, we would just go infinitely far detuned to suppress decay associated with emission and collective decay, right? And in practice, we go at some optimal detuning that's set by the collective cooperativity per atom cloud. That's optimal for maximizing the ratio of coherent interactions to collective decay. But if actually we want to focus on engineered dissipation, then it would be natural to actually put that collective decay process on resonance. And in general, in this scheme for programming the graph of interactions, right, I have some, essentially the structure of the Lindblad operators. One way to think about it is I could write down the Hamiltonian in momentum space as some like spin wave dispersion. And the structure of the Lindblad operators directly mirrors that. I think so we've operated in a regime where we try to minimize the dissipation and focus on the coherent dynamics, but it would certainly be interesting to explore the regime, and obviously you've done theory on this, where one sort of maximizes the dissipation and tries to use that as a resource.
Thank you.
Yeah, Rahul?
So I have maybe one general question. So when you're thinking about quantum simulation of all-to-all models, my intuition would be that if you have any errors in your simulator, they should spread very much and completely destroy any signature of what you're trying to simulate. So is that a concern, or how do you go around?
That's a really great question. So actually, one thing that we have thought about some is, particularly as one maybe goes to like very strong coupling and wants to do this with single atom qubits, in principle, having the ability to prepare like a graph state on any graph seems very powerful, because then by measurement you can prepare, like if it's just a 2D graph, you can prepare ground states of toric code states. If it's a fancier graph, you could, have applications to these like non-local error correcting codes. Sorry, this is a long answer. But I was going to say, I had a student who was sort of doing some analysis of how well would this work, and the question came up, well, how do I even think about it if I have correlated errors, because the dissipation is collective? And he actually came up with a clever trick for essentially designing the dynamics to ensure that the errors become uncorrelated. And so it turns out for a given graph, you'll get some collective modes. One way to sort of program in the collective modes involves programming some detunings of different atoms, essentially shifting the resonance for different atoms. And it turns out my student Avakar came up with actually a sort of an elegant scheme for choosing the combination of, I think, the detunings and the couplings to actually make sure that the decay becomes independent. And so that was actually something that wasn't obvious to me that you could do that, but it seems that there are actually clever ways to engineer things to avoid collective loss if it's a concern. So there's still going to be a question of how well, how well you do that programming. Probably.
Yeah, but I guess the statement is not much worse than if you had geometrically local interactions.
I think at least it seems like there is a way to be clever and get it to be the same. I think there's still interesting questions of, if you aren't that clever, how bad is it, right? I would love to know. Yeah.
Okay.
Yeah.
Let me add one, maybe this was more of a technical question just from my understanding. So when you say that the spin squeezing is a signature of entanglement, you're already making an assumption that you have a Gaussian state, but you also have this repulsion in your atom clouds. Does that change this conclusion? Or?
Did you say repulsion? Sorry.
Sorry, you have this U of UN squared, right?
Yeah, so, yeah, let me maybe take a step back. So the model that I wrote down that's kind of this effective Hubbard model is already actually making some approximations, but I think that the full model is just, initially, it's just a collective spin model. And there, the Gaussian approximation is a good one for us, but there are also squeezing inequalities that are specific for spins, which in the more general case one can use. So yeah.
Maybe I can ask you about that.
Yeah. So for example, I mean, the fact that you're living on a sphere, right? One has to actually know what is the coherence of the collective spin in order to calibrate how much squeezing you have. So if the coherence goes away, it's not enough to just see the noise go down, right? One needs to, and so so one has to normalize things correctly. Yeah. Yeah. That is just using the fact, no, actually it's really just using the fact that you actually say, do I have metrological gain? So can I detect, a perturbation better than I could with this many unentangled atoms? It assumes a correct atom number calibration, and we're very careful about that. And it basically says I have a phase sensitivity for an unentangled state that's, set by 1 over square root of n. Do I do better than that? That's the rough picture, yeah. Mm-hmm. So one needs to measure the noise and the coherence.
Mm-hmm. Giovanna?
So thank you, Monika. Great talk. I have a question regarding what is the limitation to the entanglement you can achieve. I can imagine the cooperativity plays a role.
Yeah. So in general, the figure of merit, if I want to kind of squeeze multiple different collective modes, is the square root of the collective cooperativity per mode. And so, for example, if I have, m sites and each of them has n atoms, and I just want to do global squeezing, then the figure of merit will be the square root of m times n. But if I want to sort of squeeze, several different spatial modes, or like independently squeeze each spatial mode, the figure of merit would just be the square root of the square root of the collective cooperativity per site. So in general, that's the figure of merit if I want kind of multi-mode squeezing.
This is the figure of merit.
And now,
It's also about the scalability of your procedure.
And so the interesting thing is in terms of scalability, as long as the sort of geometry of the cavity mode is fixed and there's room to keep adding more ensembles, I essentially, I can get the same amount of squeezing per mode, because I just add another atom cloud. I have more total atoms, but also the collective cooperativity per mode stays fixed. At some point, you have to ask about, if I want to make a really big cavity, the G is going to go down, right? The cooperativity per atom is going to go down. But that's sort of how things scale. Does that answer the question?
Yes.
Yeah.
I have another question.
Uh-huh.
This regards what you were showing about the SSH model. So I like the proposal of using interferometry. You can also look at the spectrum at the cavity output. Mm-hmm. Have you considered it, and how is it with respect to implementing the interferometry of the edge states?
So actually, we very briefly looked at kind of, rather than doing the interferometry, using the cavity to measure essentially to read out either a symmetric or anti-symmetric combination of the edges. So there are potentially ways of using the cavity. I'll just say the reason we haven't explored that deeply is that actually our cavity mirrors are somewhat lossy, and so we don't get out a very large fraction of the light. So for us, it turns out to be generally better to map the information onto an atomic signal into image in this current setup. But in general, I think there's definitely interesting directions that would involve some form of spectroscopy with the cavity. Yeah, it would be fun to chat if you have specific ideas. So, yeah. Mm-hmm.
Any last minute? Okay, Helmut.
It's more a technical question. So what's the level of control on the atom number and state that you have in your ensembles, or can you envision to have exactly the same number at some point?
Yeah. So for us, the direction that we would like to go, actually maybe just show the picture again, is in kind of our next generation cavity, where I said we think we will have a cooperativity of 200 or so. The idea will actually be to trap single atoms in tweezers, but one could nevertheless, so there's room in the cavity geometry we envision to have maybe 200 individual atoms along the, within the Rayleigh range, or a fraction of the Rayleigh range. And then you could think, I could address them as individual atoms. I also could still address them in groups and think of them as sort of mesoscopic collective spins that I can detect with single atom resolution. And I actually think that's a very interesting regime to explore, where you could deterministically say, I have 20 groups of 10 spins.
Yeah, so you build them from single ones and not have start with them.
And so, yeah, so if you build them from single ones, I think that's the best way to really have things well controlled. So, of course, there are other ways one could use, with ensembles, maybe using some feedback to make sure you deterministically have the same number. But this is the direction that we would like to move.
So currently your numbers are about 20, 25, or what is it per ensemble, or is hundreds? I don't know.
Number of atoms?
Yeah.
Oh, no, it's actually 1,000 or even thousands.
1,000 per ensemble.
Yeah.
Plus minus 100 or so.
Yeah, I'm actually not 100% sure whether we're projection noise limited on the loading, but yeah.
Okay, thanks.
But certainly there is some spatial inhomogeneity in the loading.
Yeah, that's a cool route.
So I think this is a nice, this would be a very clean system. So yeah. Mm-hmm.
Okay. So in the interest of the coffee break, let's thank Monika again. See you at 4.